Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about the module Angular Momentum from the paper Quantum Mechanics 1. So, the main points that are going to be covered in this module are definition of angular momentum. Then you will also know the angular momentum as the generator of infinitesimal rotations. Then we'll also know about the eigenvalues and the eigenvectors. We'll also develop an understanding of the ladder operators. The study of angular momentum assumes greater importance in quantum mechanics than even in classical mechanics. There could be many reasons for this. In the first place, you know from the study of Stern-Gerlach experiment that the angular momentum is quantized. Second is the observation of the existence of the intrinsic spin, angular momentum, of elementary particles like electrons, protons, etc. Thirdly is the fact that the importance of periodic motions envisaged as motion in a closed orbit involving angular momentum. A thorough understanding of angular momentum is, therefore, essential in atomic, molecular, and nuclear spectroscopy. Even in scattering and collision problems, considerations of angular momentum play important role. Angular momentum concepts have led to natural generalizations as, for instance, isospin in nuclear physics and the SU3 symmetries in particle physics. Commutation relations of angular momentum. Now, according to classical mechanics, the definition of the orbital angular momentum of a particle about the origin O is defined as angular momentum vector L is equal to the cross product of the vector r and the vector p, where the vector r is the position vector and the vector p is the linear momentum vector of the particle. Now, if we want to find out the corresponding quantum mechanical analog for the orbital angular momentum vector, then this, in case of quantum mechanics, is the orbital angular momentum operator, and this orbital angular momentum operator can be obtained by considering the dynamical variables, that is the position vector r and the linear momentum vector p, as operators. So, using the above definition of the angular momentum vector, we can see that if we want to write down the various components of the orbital angular momentum operator, then the x component of the orbital angular momentum operator L subscript x is given by operator y times operator p subscript z minus operator z times operator p subscript y, component of the radius vector operator, and operator z is the z component of the radius vector operator or the position vector operator, while operator p subscript z is the z component of the linear angular momentum operator, and operator p subscript y is the y component of the linear angular momentum operator. Similarly, the y component of the orbital angular momentum operator is given by operator z times operator p subscript x minus operator x times operator p subscript z, where again operator x gives the x component of the position vector, while operator p subscript x gives the x component of the linear momentum operator. And similarly, we can write down the z component of the orbital angular momentum operator, which is given as operator x times operator p subscript y minus operator y times operator p subscript x, and these three components of the orbital angular momentum operator are obtained from the above definition of the orbital angular momentum. And if we want to write down these three different equations in a common form, then we can write this down as operator L subscript I, where the subscript I denotes the component of the orbital angular momentum operator being considered, is equal to the rank 3 tensor epsilon ijk, that is epsilon subscript ijk, times operator x subscript j times operator p subscript k, where the operator xj takes the value x subscript 1 and so on, depending upon the value that j takes, and operator p subscript k takes the value operator p subscript 1 and so on, depending upon the value that k takes. And the third rank 3 tensor epsilon ijk basically gives the indices ijk, where the index I corresponds to the component of the orbital angular momentum operator, index j corresponds to the component of the position vector operator, and index k corresponds to the component of the linear momentum operator. And using the commutation relations between the position vector operator xj and the linear momentum vector operator pj, that is, if we have the commutation relation operator x subscript I and operator p subscript j, then this commutation relation is equal to iota times h cross times delta ij, where h cross is h by 2 pi and h is the Planck's constant, and delta ij is the Kronecker delta, where if the index I is equal to index j, then it gives a 1, otherwise it gives the value 0. Thus, from these relations, one can show that the commutation relation for the operator x subscript I and the operator x subscript j is equal to 0. One can also show that the commutation relation of the operator L subscript I and the operator L subscript j is equal to iota times h cross times epsilon subscript ijk whole times operator L subscript k. And also one can show that the commutation relation of the square of the angular momentum operator, orbital angular momentum operator, with its k component, that is the commutation relation of operator L square with operator L subscript k, is equal to 0, where the index k takes the value 1, 2, 3, and where the square of the orbital angular momentum operator, operator L square, is equal to operator L subscript x square plus operator L subscript y square plus operator L subscript z square, where operator Lx, operator Ly, and operator L subscript z are the x, y, and z components of the orbital angular momentum operator. Rotations in coordinate space. Angular momentum as generators of infinitesimal rotations. Now let us analyze the connection of the angular momentum operators with rotations in space by considering the change in representation when coordinate system S, x, y, z is rotated about the z-axis to the system S prime with origin O and the coordinates x prime, y prime, z prime by an angle theta. That means that supposing if we have an original coordinate system denoted by the coordinate system S, having its origin at O and having the coordinate axis x, y, and z, and if this coordinate system is rotated through an angle theta about the z axis so that the origin remains unchanged, and the new coordinate system S prime is denoted by the coordinate axes x prime, y prime, and z prime, where z prime and z are identical, then for such a rotation, if we have a position vector denoted by position vector r having coordinates x, y, and z in the S coordinate system, this position vector r will transform under this rotation to the position vector r prime, as a function of coordinates x prime, y prime and z prime in the s prime coordinate system, where the new coordinates are given by the relation x prime is equal to x times cos theta plus y times sin theta, where x and y are the coordinates of the original coordinate system, that is S, and theta is the angle of rotation from the original x-axis in the xy plane towards the y-axis. Similarly, y prime, that is the coordinate in the new coordinate system S prime, is given by minus x times sine theta plus y times cos theta, where, as mentioned earlier, x and y are the coordinates of the original coordinate system, that is S, and theta is the angle of rotation, while z prime turns out to be equal to z since the rotation was effected about the z-axis, so the z-axis remains invariant. Now, the wave function psi prime describing the rotated state having the position vector r prime must be equal to the original wave function psi having the position vector r, that is, the wave function psi prime as a function of position vector r prime should be equal to the wave function psi as a function of position vector r, generator of infinitesimal rotations. Now, the example that we were just considering regarding rotation in coordinate space about the z-axis from the coordinate system S having origin O and coordinates x, y, z to the coordinate system S prime having origin O and coordinates x prime, y prime and z prime, undergoing a rotation theta in the xy plane from the x-axis. If we substitute for the position vector r prime, assuming that the rotation given by the angle theta is infinitesimally small, we can write the wave function in the new coordinate system, that is psi prime as a function of coordinates x prime, y prime and z prime as psi prime as a function of x plus y theta, then coordinate y minus x theta and coordinate z. And this should be equal to the wave function psi as a function of coordinates x, y, z in the original coordinate system. So here what we have done is that the equations for x prime and y prime, we have, assuming that our theta is infinitesimally small, sine theta has been approximated as theta, while cos theta has been approximated as 1. It is, however, more convenient to replace x by x minus y theta and y by y plus x theta on both sides, which will yield the result psi prime as a function of coordinates x, y and z is equal to the wave function psi as a function of coordinates x minus y theta, comma, y plus x theta, comma, z. So what we have done is that instead of writing psi prime as x plus y theta, comma, y minus x theta, comma, z, we are now writing the wave function psi prime as function of coordinates x, y, z, and the wave function psi is now being represented by the corresponding coordinates, which are denoted by x minus y theta, comma, y plus x theta, comma, z. Using the Taylor series expansion for the wave function psi on the right hand side of the above equation, we have the wave function psi prime in the coordinate system S prime given by wave function psi prime as a function of coordinates x, y and z is equal to wave function psi as a function of coordinates x, y and z plus theta times bracket open minus y times partial derivative with respect to x plus x times partial derivative with respect to y bracket close, wave function psi as a function of coordinates x, y, z plus some additional terms, and here assuming that the additional terms, which would basically be higher order terms in theta, are extremely or infinitesimally small, since our theta is also infinitesimally small. Therefore, in this expansion, that is Taylor series expansion for psi, we only retain the first term of the expansion, So we note that the differential operator on the right can be identified as the z component of the angular momentum operator, that is operator L subscript z, which is given by minus iota times h cross times bracket open x times partial derivative with respect to y minus y times partial derivative with respect to x bracket close. Thus, the above equation can be written as psi prime as a function of coordinates x, y, z is equal to bracket open 1 plus iota times theta times operator L subscript z by h cross bracket close whole times wave function psi as a function of coordinates x, y, and z. Where basically what we have done is that in the above equation, we have taken the wave function psi as a function of coordinates x, y, z as common on the right hand side, and within brackets we have replaced the second term with the z component of the angular momentum operator, doing the necessary transformation, and thereby showing that the z component of the orbital angular momentum operator, that is operator L subscript z by h cross, plays the role of the generator of infinitesimal rotations, adopting general view of angular momentum. Now, the example that we just discussed regarding the rotation of a coordinate system with coordinates x, y, z to a coordinate system S prime having coordinates x prime, y prime, and z prime undergoing a rotation of angle theta about the z axis with the origin remaining unchanged, we can generalize this result to the rotations that is along the unit vector n, and the general result can be written as the wave function psi prime as a function of position vector r is equal to 1 bracket open 1 plus iota times theta times unit vector n dot orbital angular momentum vector L whole upon h cross bracket close times psi as a function of position vector r. And for rotation through a finite angle theta, we can sum up the series and can express the final result as given by psi prime as a function of position vector r is equal to exponential to the power within brackets iota times theta times unit vector n dot L vector upon h cross, where unit vector n, where we have taken the scalar product of the unit vector n and the orbital angular momentum L, this whole times the wave function psi as a function of position vector r. Important point that one needs to note over here is that the origin of the commutation relation lies in the geometric properties of rotation in three-dimensional space, and that these relations are very general, including the relations for the x component, the y component, and the z component of the orbital angular momentum operator denoted by operator L subscript x, operator L subscript y, and operator L subscript z, which may be considered as a special case. So one can adopt a more general view, and then one can use the symbol operator J for the angular momentum operator with the components of the orbital angular momentum operator or the total angular momentum operator given by operator Jx, operator J subscript y, and operator J subscript z, which are correspondingly the x, the y, and the z component of the orbital angular momentum or the total angular momentum J. Adopting a more general view, we can use the symbol operator J to denote the total angular momentum operator having the components operator J subscript x, operator J subscript y, and operator J subscript z, where operator J subscript x is the x component of the total angular momentum vector, operator J subscript y is the y component of the total angular momentum operator, and operator j subscript z is the z component of the total angular momentum operator. And using these components, one can also define the commutation relations for the total angular momentum operator j. So the commutation relation for the total different components of the total angular momentum operator j are given by commutation relation of the operator j subscript x and operator j subscript y is equal to iota times h cross times operator j subscript z, where operator j subscript x is the x component, operator j subscript y is the y component, and operator j subscript z is the z component of the total angular momentum operator respectively. Similarly, the commutation relation between the y and the z component of the total angular momentum operator is given by operator commutation relation of operator j subscript y and operator j subscript z is equal to iota times h cross times operator j subscript x, and the commutation relation for the z and the x component of the total angular momentum operator, that is commutation relation for operator j subscript z and operator j subscript x, is given by iota times h cross times operator j subscript y, where operator j subscript y is the y component of the total angular momentum operator. Further, the square of the total angular momentum operator j operator vector square is given by operator j subscript x square plus operator j subscript y square plus operator j subscript z square. That is, it is the sum of the square of the x, y and z components of the total angular momentum operators. Further, one can also show that the commutation relation between the square of the total angular momentum operator and the components of the total angular momentum operator, that is the commutation relation between operator j square and operator j subscript x, or operator j square and operator j subscript y, or operator j square and operator j subscript z, all turn out to be equal to 0. Eigenvalues and eigenvectors of the operator j. We now show that these commutation relations determine the quantal properties, that is the eigenvalues and eigenvectors of angular momentum operators. Since the components of the angular momentum operators do not commute amongst themselves, one cannot find a common basis for all the three components. However, because the operator j square, that is the square of the total angular momentum operator, commutes with the operator j, that is the j square operator commutes with the angular momentum operator j, we can have a common basis for the operator j square and any one component of the operator j. Let's say the operator jz, or the z component of the operator j. Eigenvalues and eigenvectors of operator j square and operator j subscript z. So now let us note that the eigenvalues of the operator j square and the operator j subscript z, that is the z component of the total angular momentum, are real because they are Hermitian operators, and we know that for Hermitian operators their eigenvalues are always real. Thus, it is possible to find a complete set of simultaneous eigenstates of the operators j square and the operator j subscript z. So let us now represent such a common basis representing the simultaneous eigenstates by the state Jm, where J refers to the eigenvalues of the total angular momentum operator j square and M refers to the eigenvalues corresponding to the operator j subscript z, where operator j square is the square of the total angular momentum and operator j subscript z is the z component of the total angular momentum operator. Now, the state vectors denoted by the ket vector Jm form the orthonormal set, that is bra j prime m prime ket Jm is equal to delta subscript j j prime delta subscript m prime, where delta is the Kronecker delta and gives 1 when the indices occurring in the subscript are equal, and gives 0 when the indices occurring in the subscript are not equal. Thus, by definition, one can write operator j square acting on the basis jm gives h cross square times lambda j times the basis jm, where h cross square times lambda j are the eigenvalues. Similarly, operator jz acting on the basis jm gives h cross times m times the basis jm, where h cross times m is the eigenvalue for the operator jz. Also, it is important to note over here that the operator j square, being the sum of the square of the Hermitian operators, is positive definite. Therefore, the eigenvalues corresponding to the operator j square given by lambda subscript j is given as ket state jm, operator j square acting on the bra state jm, operator j square acting on the ket state jm, whole divided by h cross square is greater than or equal to 0. Ladder operators. Using the relations defined above, one can clearly see that bra state jm, operator j square acting on ket state jm, which is equivalent to the complete value or the mean value of the operator j square, and this is equal to the mean value of the operator j subscript x square plus the mean value of the operator j subscript y square plus the mean value of the operator j subscript z square, and this is greater than equal to the mean value of the operator j subscript z square. That is, if we substitute the eigenvalues for the mean value of the operator j square and the operator j subscript z square in the above equation, then we get lambda j times h cross square is equal to mean value of the operator j subscript x square plus mean value of the operator j subscript y square plus m square h cross square. And since the operator j subscript x and operator j subscript y are Hermitian, and also that the operator j subscript x square and the operator j subscript y square are positive and their expectation values are also positive, therefore it follows that the eigenvalues denoted by lambda j are greater than equal to the eigenvalues denoted by m square are greater than equal to 0, where the eigenvalues lambda j correspond to the operator j square, while the eigenvalues m square correspond to the operator j z square. Now the next step is to introduce what are called the ladder operators. So let us now define two operators as operator j subscript plus is equal to operator j subscript x plus iota times operator j subscript y, and operator j subscript minus is equal to operator j subscript x minus iota times operator j subscript y. The commutation relations given above can be easily expressed as the commutation relation of operator j subscript z with the operator j subscript plus is equal to h cross times operator j subscript plus. Similarly, the commutation relation of operator j subscript z with operator j subscript minus is given as minus h cross times operator j subscript minus. And using the above relations, one can also write the commutation relation for operator j subscript plus and operator j subscript minus given as twice h cross times operator j subscript z. So one can note over here that the operator j subscript plus and operator j subscript minus are not Hermitian operators, but instead operator j subscript plus dagger, that is the adjoint of operator j subscript plus, is equal to operator j subscript minus, and similarly the adjoint of operator j subscript minus, that is operator j subscript minus dagger, is equal to operator j subscript plus. As a result, we now express operator j square equal to operator j square subscript x, operator j square subscript y plus operator j subscript z square, and this is equal to operator j subscript minus operator j subscript plus h cross times operator jz plus operator j subscript z square, and this can then be written as, using the above results, operator j subscript plus times operator j subscript minus h cross times operator j subscript z plus operator j subscript z square. Effect of operator j subscript plus and operator j subscript minus on the state Jm. Now, since we have seen that operator j subscript plus and operator j subscript minus are not Hermitian operators, but operator j subscript plus and operator j subscript minus both commute with the operator j square, it is therefore easy to show that operator j square acting on operator j subscript plus acting on the state Jm gives h cross square times lambda j times operator j plus acting on the state m. Similarly, operator j square acting on operator j minus acting on state Jm gives operator h cross square times lambda j times operator j minus acting on state Jm. Now, the operator j subscript z, that is the z component of the total angular momentum operator, acting on the operator j plus or operator j minus acting on the state Jm, can be worked out as operator j subscript z acting on operator j plus acting on the state Jm is equal to operator j plus acting on operator j subscript z plus h cross times operator j plus whole within bracket acting on the state Jm, and this gives us the result within brackets m plus 1 times h cross times operator j plus acting on the state Jm. Similarly, operator j subscript z acting on operator j subscript minus acting on the state Jm can be given as operator j subscript minus acting on operator jz minus h cross times operator j minus the whole within bracket acting on the state Jm, and this turns out to be equal to within brackets m minus 1 whole times h cross times operator j minus acting on the state Jm. From these two relations for the operator j subscript plus and operator j subscript minus and the operator jz acting on them for the state psi for the state Jm, one can see that operator j subscript plus acting on the state Jm is an eigenvector of the operator j subscript z with eigenvalues within brackets m plus 1 whole times h cross, whereas the operator j subscript minus acting on the state Jm is the eigenvector with eigenvalues m minus 1 whole times h cross for the eigenvector j subscript z. Using both these relations, one can then conclude that operator j plus acting on the state Jm produces a state j comma m plus 1, while operator j minus acting on the state Jm yields the state j comma m minus 1. It is therefore possible to write operator j plus acting on state Jm is equal to c subscript Jm dagger c subscript Jm plus superscript plus times h cross times state j comma m plus 1, while operator j subscript minus acting on the state Jm is c subscript Jm superscript minus times H cross times state j comma m minus 1, where C subscript jm superscript plus and C subscript jm superscript minus are normalization constants, raising and lowering operators. Notice that while the raising operator j plus acting on the state jm increases the eigenvalue of the operator j by 1 unit, the operator, that is the lowering operator j minus, lowers the state by m minus 1 and reducing the eigenvalue of the operator jz by 1 unit. That is why they are called raising and lowering operators. Repeated operation of the operator j plus, that is the raising operator, on the state shows that the given state jm would go on increasing the index of m to m plus 1, m plus 2, m plus 3 and so on. Similarly, the lowering operator j minus would go on lowering the values to m minus 1, m minus 2, m minus 3 and so on. Clearly, the series must terminate. Otherwise, we would have vectors like j, m prime which violate the inequality obtained above. In order to terminate the series, let there be a maximum value m2 such that for which the operator j plus acting on the state j m2 is equal to 0. Similarly, for a minimum value m1 such that when the lowering operator j minus acting on the state j m1 gives a 0. So, applying the lowering operator to the first and the raising operator j plus to the second, we get j minus m2 times within brackets m2 plus m1 is equal to 0, and lambda j minus m1 times m1 minus 1 within brackets equal to 0. Eliminating the value of lambda j from these two equations, we find that m2 plus m1 times within brackets m2 minus m1 plus 1 is equal to 0. Since m2 is greater than or equal to m1, the only possible solution is m1 is equal to minus m2, as the maximum value that m2 can take is j. We have m2 minus m1 equal to twice of j, where twice of j is a non-negative integer, and therefore j can take the values 0, half, 1, 3 by 2, 2 and so on. Eigenvalue spectrum of angular momentum. Thus, for a given value of j, the permitted values of m lie between minus j is less than equal to m is less than equal to j. That is, m can take values from j, j minus 1, j minus 2 to so on to 0 to minus j plus 1 and minus j. Now, substituting for m subscript 2 in the equation that we have discussed above, for lambda subscript j, we get lambda subscript j is equal to j times within brackets j plus 1, and as seen before, m can take the values from minus j to plus j, with each value differing from the other value by an integer. Finally, we get the result operator j square acting on the state jm yields h cross square times j plus 1 within brackets whole times state jm, where h cross square times j plus 1 is the eigenvalue corresponding to the eigenvector j square and the eigenstate jm, while the operator jz acting on the state jm yields h cross times m times state jm, where h cross times m is the eigenvalue for the eigenvector operator jz acting on the eigenstate jm. Thus, we have obtained the eigenvalue spectrum of the angular momentum operator j. by starting from the commutation relations between the different components of the total angular momentum operator and using the basic postulates of quantum mechanics. It is remarkable to note over here that the half integral values of the angular momentum J have emerged from this general treatment in a natural way. And as we know from before, that the half integral values of the angular momentum J are associated with the spin of the particles. So students, now let us summarize what we have learned in this module. Firstly, we learned how to define the orbital angular momentum operator and write down the commutation relations between its components. Having done that, we could then identify the angular momentum as a generator of infinitesimal rotations in three-dimensional space. Then, from this, we gathered the knowledge of the origin of commutation relation and realized that the origin of commutation relations lies in the geometric properties of rotations and the need to generalize the definition of angular momentum. We also showed that the commutation relations determine the quantal properties of the angular momentum, that is, the eigenvalues and eigenvectors of the angular momentum operator. And then we also learned the significance of ladder operators, or what are also called as the raising and lowering operators, and we found out that for these operators we have to define the upper and the lower limit. Thank you.